Oh, great.
Okay.
Great, thanks.
Let us begin our seminar. And today our speaker is Professor Roberta Musina from the Udine University. Please, Roberta.
Oh, thank you. Okay, first of all, of course, let me thank my colleague, collaborator, and friend, Alexander Nazarov, for this kind invitation. This is perhaps my third or fourth talk in Smirnova seminar. So I'm so happy. This is, in fact, as I wrote in the abstract, a survey talk about the so-called Hardy-Sobolev-Maz'ya inequality. In fact, I will not report on some recent results of mine. Rather, I would like to try to draw your attention on some of the results that have been obtained about those inequalities and the related problem in the first decade of the present century. But, and also I wanted to draw your attention on some questions that are still open up to now, despite the fact that this problem have been largely studied. So many papers refer to this problem and related questions. Okay, these are dilation invariant inequalities for functions defined on the Euclidean space. And here is perhaps the most popular and perhaps in a sense important in dilation invariant inequality. It is the Sobolev inequality, which holds whenever the exponent p is between 1, okay, 1 is included, but don't mind, and the p. In this case, we have the critical Sobolev exponent, and this inequality holds with an explicitly known best constant S. Also, the extremals for this inequality are completely satisfied. They are explicitly known, and in a sense, a uniqueness result holds in the sense that up to dilations, up to multiplications by constant, and up to translations, there is unique radially symmetric function u for which this inequality becomes an equality. Also, Hardy type inequalities are very popular and largely studied. Here, a new parameter, k, appears. K is an integer between 1 and d. In fact, in this talk, I will be mainly concerned with the case when k is smaller than d. And in this case, the space Rd, which is this space, is the cross orthogonal product of two subspaces. And any point in Rd has two coordinates. In particular, the second coordinate runs in a k-dimensional space, and the absolute value, the norm, Euclidean norm of y gives you the distance of zeta from this subspace of codimension k, which will be our singular set. Of course, if k is equal to d, then we only have one coordinate and the singular set reduces to the origin. Next, let us introduce a new parameter, a real parameter, but we take a large enough so that this inequality holds true. And in this case, it is well known that this Hardy type inequality hold with a best constant in the left-hand side. In fact, this is nothing but the Hardy inequality for functions of k variables, and then you integrate in the remaining variable, in the last variable x, say. A remark, this assumption is needed And it is equivalent to say that this weight is locally integrable. Of course, this weight is worse, that is more singular than this one at the origin. So we have this equivalence between the large strict inequality and the integrability property of the weight here. Next, let us play with those two inequalities for a given fixed parameter A such that k plus A is greater than P. This is just an exercise. In this case, this leading term bounds are weighted LP norm of U, but it also bounds this weighted LP star norm of U. The computations are very easy thanks to the Sobolev inequality and thanks to the Hardy inequality, which holds because of this assumption. But in fact, we have a full family continuum, a continuum of Hardy-Sobolev type inequalities, just thanks to very simple Hölder interpolation, which is the conclusion of those very simple computation. The conclusion is as follows. Assume that magenta assumption is satisfied, which is equivalent to say that the Hardy inequality holds. Then, no matter, you can take any Q, and for any Q, this dilation invariant inequality holds. I gave a name to this blue constant because it will appear many times in this talk. It's evident that because of this assumption, the constant HA is strictly positive. Two simple remarks about this conclusion. Because of the magenta assumption, the weight, all the weights are locally integrable, and in particular, given P, given A, this is the only exponent you can put in the left-hand side if you want to have that this inequality holds for any positive constant, for some positive constant C, because C is zero. I mean, if you want to have C not zero, then the left and the right-hand side must have the same rescaling properties. And this is the unique choice of the exponent here. Of course, also those two assumptions are needed because we are dealing with unbounded domains and because of Sobolev embedding theorem. Q certainly cannot be greater than the Sobolev exponent. But now the question is, are we really happy with this additional assumption and hence with this conclusion? The answer is it depends, not always. We are happy when we are dealing with spherical weights, that is when K is equal to D, the singular set reduces to the origin, when that is when the weights you are interested in are precisely powers of the distance from the origin. The magenta assumption became like this, and the conclusion I wrote in the previous slide says that, okay, this inequality holds for any trial function U and for C with positive not depending on U. And this is in fact a particular case of a larger class of interpolation inequalities, which have been first proved by Ilin in my birth year, but which became very popular, so popular with this paper by Caffarelli con Nirenberg. And I have to say that a lot of work have been done about the inequality I wrote here and about also the more general interpolation inequalities by Ilin, Caffarelli, Kohn, and Nirenberg. I will be mainly concerned with the case when K is strictly smaller than D, but let me emphasize this fact which concerns spherical weight. The assumption we started with is this one, magenta, which is equivalent to say that the Hardy inequality holds, and it is also equivalent to say that all the weights in this inequality are locally integrable. And it is also equivalent to say that all those dilation invariant inequalities hold with a positive constant. Roughly speaking, Hardy, if and only if, Hardy-Sobolev, very roughly speaking. Now, let us consider the case of cylindrical weights. So K is strictly smaller than D. The weights are powers of the distance from a non-trivial space. Here is the constant. In blue, the conclusion we had in the previous slides told us that this inequality hold, which is true for any given exponent Q, you can find some positive function constant here. But in this case, the magenta assumption is not needed to have that the weights are locally integrable. In fact, the weight we find here is locally integrable provided that this blue assumption hold. This is a difference with respect to the spherically symmetric case. Before describing the picture I've tried to draw here, let me notice that if you compare this assumption on Q with this assumption on Q, Q appears here for given A, and if you want to find a Q which satisfies both of those two assumptions, then you are forced to take A not smaller, or in fact you have to take A greater than this negative number which is written here. What is this dotted red line is the hyperbola in which you lose the local integrability of the weights. But if for A greater than this number, okay, you always can find Q. And if Q is large enough but smaller than the critical Sobolev exponent, you find up here weights that are locally integrable, but the magenta assumption tells us that we are in this pink unbounded half strip. So the question was, are we happy with the conclusion star? No. Why? Because we do not understand why the inequality star does not hold, shouldn't hold in this blue area, and in fact it holds in this blue area, and this is what Maz'ya proved. So this is a theorem by Maz'ya, which is already in the first version of his book, German, and it holds under, okay, he states his theorem in the under the assumption D small greater than P, but something can be said also for D smaller or equal than P, don't mind. All the assumptions you can see here, this, and this are needed, are necessary and sufficient to have that this inequality M holds with a positive constant in the left-hand side. M is, of course, because of Maz'ya. This is, in fact, not Musina. This is, in fact, just an application, a corollary of a much more general theory in this book by Maz'ya, in which some isoperimetric inequalities are related to Sobolev inequalities and then to Hardy-Sobolev inequalities. I cannot enter into those details. Again, I say that Maz'ya's theorem gives a complete answer in the blue area. Next, once one has integral inequalities, perhaps one is lead to see whether, for instance, functions U achieving the best constant exist in a suitable energy space or not. And this will be our next and perhaps main step. So if A is greater than this negative number I showed you the picture before, then thanks to Maz'ya's inequalities, this is a norm. This is a norm on functions, smooth compactly supported functions. And it is a uniformly convex norm indeed. So you can plainly define this nice reflexive Banach space, which is Sobolev weighted, say, Sobolev type space, homogeneous, because here we use only the norm, weighted norm of the gradient. And by Maz'ya inequalities, we have that all those embeddings holds, provided that Q is large enough. The Maz'ya constant, the best constant in Maz'ya's inequality, is therefore given by this infimum. So here we have a nice minimization problem. And let me also write here the Euler-Lagrange equations that are related to this minimization problem. What does it mean? It means that any minimizer for the Maz'ya constant is a solution of this differential equation, of course, up to a Lagrange multiplier. We can assume that U is non-negative and also that solves this equation up to a Lagrange multiplier. We can eliminate in a sense. U will be a weak solution of this equation, or if you prefer, you can read this equation in the dual space of the 1P. The differential operator we have here is a sort of weighted P Laplace operator. Is weighted if A is not zero. So our next, the next step is concerns the existence of minimizers, a solution of this minimization problem, and or also something will be said about the positive non-negative solution of this differential equation. But before that, let me say, okay, the constant HA, which appears here, it was D minus P plus A over P. And when you take as Q, the highest possible exponent, which is the Sobolev critical exponent, then the ratio in the definition of the Maz'ya constant takes this form because of the expression of this constant blue constant here. And of course, trivially, if in addition A is zero, then the Maz'ya constant at the critical level is the Sobolev constant, and it is achieved by Obentalenti type functions. That's totally trivial. What about the existence of extremals, of solutions to this minimization problem? Moment, before I have to present this list of references. Surely this list of references is not complete. A lot of work have been done about the Maz'ya constant, existence of extremals, their qualitative properties, and so on and so forth. I list them, I listed here few of those papers, starting with this paper by Badiale and Gabriella Tarantello, 2002, but you can see that there is a big temporary hole in time here from 2009 and 2024. In fact, the only say recent paper in this list is this paper by Ling and Ma, in which some result by Mancini and Deep have been extended in the partially extended in the non-Hilbertian case, but don't mind. I've tried to look for in the literature for new, more recent results, but I wasn't able to find them. So please, if you know more recent results, please let me know. Okay, axis. Oh my God. What does it happen? Can you hear me?
Yes.
Okay, thank you. Okay, existence of extremals for the Maz'ya constant. We will not be involved with the case when A equals to 0 and Q is the critical Sobolev exponent, of course. As far as I know, this is the most complete result, valuable result. Surely before then, 2009, some existence results have been already improved, in particular in the Hilbertian case P equals 2. Okay, the result, the existence result, which is not properly an existence result, looks quite standard. If Q is below the critical Sobolev exponent, then, despite the fact that there always exists non-compact minimizing sequences, in fact, the Maz'ya constant is achieved. Something more can be said. It can be said that any bounded minimizing sequence basically has a compact subsequences up to rescaling. The critical case is more difficult, and but the result in I and in II is, say, almost standard. The Maz'ya constant is always bounded from above by the Sobolev constant, and the strict inequality is a necessary and sufficient condition to have the compactness up to rescaling of all the bounded minimizing sequences, basically. And in particular, if the strict inequality holds, then the Maz'ya constant is achieved. Here I add also this result, which provides a sufficient condition for the validity of the strict inequality. In this paper with Marita Gazzini, the third statement is just obtained by testing the Maz'ya constant with the O'Bentalenti type function, which is radially symmetric, despite the fact that the weights are not radially symmetric. The computation goes nicely, and we obtain this result. Great. The conjecture might be as follows. The conjecture might be that if the weight here is, say, continuous, if A is positive, then in a strict inequality, the equality holds and the Maz'ya constant is not achieved. If A is negative, straight inequality. The conjecture is if A is very big and positive, then equality holds and the Maz'ya constant is not achieved. I should say that I'm not sure that this conjecture has a positive answer also in the radially symmetric case. It might be that is open also in the radially symmetric case. But this conjecture here has a positive answer in the radially symmetric case as well as in the cylindrically symmetric case we are dealing with. Why? Because in the Hilbertian case, when P is equal to 2, here, a very simple functional change allows you to write this ratio in an equivalent way for so that you can infer a lot of informations. Now I will describe this natural function change of variable. Before, let me recall that we assume this is a necessary condition on the exponent a, but we will be here mainly interested in positive exponent a, so no troubles. To simplify notation, I introduce this real number lambda, which depends on the parameter a, and to simplify notation, I denote by sigma naught the singular set. Now, if you take any function u smooth and compactly supported away from the singular set, y equals to 0, then you can go from u to v, for instance, and vice versa, and to find that also v is smooth and compactly supported outside the singular set, so that you can plainly use the integration by parts and say that this ratio is equal to this ratio for any given u, and vice versa. Lambda a is precisely this number. This inequality is trivial, and this strict inequality comes from Maz'ya's result, basically. Okay. Sometimes it's okay. A first corollary of this simple remark is explained here. This has been already pointed out by Maz'ya in his book. If you take A to be precisely 2 minus k, then you obtain, of course, a vertex in this parabola in the variable a, and the number lambda a is precisely k minus 2 over 2 squared, which is not very interesting if k is equal to 2, of course, because in that case this is nothing but the standard Sobolev inequality. But if k is 1 or k is greater or equal than 3, then this is the best constant in the appropriate Hardy inequality. Okay, in particular, this is more interesting perhaps, in particular, in the case when k is equal to 1, we infer that this inequality holds. So the constant became 1/4. And since in case k equals to 1, the space Rd is disconnected by the singular set, we can plainly infer that this inequality holds. Rd plus is, for instance, the upper half space in Rd. This is an improvement of the Hardy inequality because 1/4 is the Hardy constant for functions with support in the half space, and it might also be seen in some cases, so we shall see, an improvement of the Sobolev inequality in a sense. Next, let us go back to this inequality. This is the same inequality I wrote, inequality and then equality I wrote before. Trial functions, the support of trial functions are far from the singular set, but we can couple this remark with a density lemma. The proof of this density lemma is not difficult. Some little bit care is needed when k plus a is precisely 2, but don't mind. If k plus a is greater or equal than 2, which is this 2, then this space of trial functions is dense in C-infinity with compact support of Rd. And so this inequality becomes inequality. And this inequality comes from, say, the theorem. So in this case, we infer this fact. Now, what is lambda? Lambda is some number you can understand depending on A. Now you can understand that if minus lambda A is greater or equal than 0, then this infimum is bounded from below by the Sobolev constant. More precisely, when the constant here is greater or equal to 0, in two cases, surely when k is greater or equal than 2 and a is greater or equal than 0, or when you are in this situation. Of course, you have to take into account this starting assumption. What can we infer by this lemma and this very simple remark? We can infer this result, which is a non-existence result, in fact, because the general theorem, which holds also in the non-Hilbertian case, says you that if A is negative, then the Maz'ya constant is below the Sobolev constant. This is the graph of the Maz'ya constant, qualitative, very qualitative graph. Here you find the Maz'ya constant. And if k is greater or equal than 2, then the remark before gives you that Maz'ya constant coincides with the Sobolev constant. It is not achieved. The same if k is equal to 1, but in that case, you have to take a greater or equal than 2 to have that the Maz'ya constant is not achieved. And next, one has to understand what does it happen when a is between 0 and 2 in the case of a singular set having codimension 1, in the case of basically half spaces. The answer goes as follows. The answer is that in case when the dimension d is greater or equal than 4, then the Maz'ya constant is achieved for any a between 0 and 2. And this is in fact, okay, perhaps there are more proofs, but in the appendix of this paper, this is proved because by using a Bresis-Nirenberg type effect. The proof of this goes as follows. Let me see the time. The proof of this goes as follows. K is equal to 1, so the singular set is in hyperplane, and we will we can take a domain omega, which is contained, for instance, in the upper half space, compactly contained in the upper half space. Great. How can we bound from, so we have to prove that the Maz'ya constant is smaller than something. We bound from above the Maz'ya constant by choosing only trial functions which have support in this set omega. Then we can use the functional change I showed you before. This is now the constant lambda A. For a between 0 and 2, the constant lambda A is positive. Thus, and not only, we also have that on the domain omega, which is something like this, the weight here is bounded from below, because omega is far from the singular set. In conclusion, by gluing together those two information, you can find a positive number C for which the Maz'ya constant is bounded by this infimum. And in the milestone paper, Brezist and Nuremberg observed that this infimum is smaller than the Sobolev constant, provided d is greater or equal than 4. What about the case in which d is the critical dimension 3? And this is what I can say up to now. In dimension d greater or equal than 3, you have non-existence for a greater or equal than 1. You can see that the situation is very different with respect to the case when d is larger than the critical dimension in the sense of Brezist-Nuremberg. As far as I know, at least I wasn't able to find in the literature results about this case when a is between 0 and 1. Okay, this also is nothing but a remark in one of those two, the appendix of one of those two papers, I don't remember which one, because in fact the non-existence is a corollary for a greater or equal than the one, a corollary of some results. For instance, one can use the result in this paper by Ben-Gurion, Frank, and Loss, who showed that for a equals 1, you have non-existence. But then it is easy to conclude for any a greater or equal than 1. But actually, in those two papers, I used to prove these non-existence results, we used another functional change, and this very remarkable and surprising result by Mancini and Sandeep. Okay, you have a variation, no problem. You find another functional change. You move from the Euler-Lagrange equations for the Maz'ya constant to this, to an Euler-Lagrange equation, to a PDE for functions defined on the hyperbolic ball. The result by Mancini and Sandeep tells us that no matter which is the value of the parameter mu, in any case, this simple unweighted equation on the hyperbolic three-dimensional space does not have any energy solution, any solution in a suitable energy space. Okay, let me say that this result does not hold in the hyperbolic d-dimensional ball with d greater or equal than 4. In dimension 3, the critical Sobolev exponent is 6, by the way. So this is 2 star minus 1. And in dimension d greater or equal than 4, it is possible to find mu such that this equation has a solution. This ends everything I decided to say about the existence. Let us go with symmetry, discussing symmetry of solutions. Of course, the weights we are involved with are not radially symmetric. So if you if we think that the extremals of the Maz'ya constant, whenever they exist, should enjoy some symmetries, then we could suspect at most that extremals has to be cylindrically symmetric, which is explained here. Surely the Maz'ya constant, the true Maz'ya constant is always smaller or equal than this Maz'ya constant for cylindrically symmetric function. The problem is to find if this is an equality or if symmetry-breaking phenomenon occurs. Differently from the case, spherical case, when k is equal to d, it is very hard to compute explicitly the Maz'ya constant, but also this Maz'ya constant on symmetric functions. Why? Because, okay, if U achieves the Maz'ya constant, then it solves up to Lagrange multiplier this PDE. And if in addition U is cylindrically symmetric, then it can be identified with a function of two variables, which solves a PDE on two variables. In the radially symmetric case, you obtain an ODE, which is basically perhaps more easy to handle. What can we say about symmetry? Okay, first tentative is to use rearrangement that works in this case, A equals to 0, so you have no weights in front of the leading term. And this is a remark in this paper by Sekis, Maz'ya, Willem. They first use the arrangements in the x variable, then in the y variable, and they end up with this result. But now a deeper question arises, so we are wondering if all the minimizers for the Maz'ya constants, if they exist, are cylindrically symmetric or not. That is a more deep question. And the answer at the end is yes. Again, in case of A equals to 0, when the Euler-Lagrange equation are driven by the standard Laplace operator. And this is, at the end of the story, a result by Isabella Mancini, Fabri, Mancini, Sandip, JDE 2006. Any solution in this case is cylindrically symmetric because of the moving plane method, basically. And from this, they also infer the uniqueness of solutions to the corresponding PDE. Of course, uniqueness, again, up to the scaling. There is a very special case in which, again, A equal to 0, P is equal to 2, as in this paper, those two papers by Mancini, Gianni Mancini and collaborators. There is this very special case, the case in which you choose A equals 0 and Q to be equals to this exponent, which is, by the way, the critical exponent in Trey's theorem. The assumptions we need is that K must be greater or equal than 2, otherwise you cannot take this exponent. Why? Because for this choice, the Maz'ya constant is the infimum of this ratio. So the exponent of y is 1 over y. The weight is 1 over y. Here is the Euler-Lagrange equation. And why this case is very special, it's because by direct computation, you see that this function U naught is a solution of the Euler-Lagrange equation. And so one can suspect that this U naught is one of the minimizers of the Maz'ya constant. In fact, it is the only minimizer of the Maz'ya constant, again, up to rescaling. Also, the non-degeneracy have been proved by Mancini and collaborators say. This very particular case have been studied also by Cao and Yang Li. I have no time to describe. They have results under weaker assumptions, symmetry results about weaker assumptions. And in this paper, Cao and Yang Li raised also this conjecture, which gives you uniqueness of U when U in a larger class of trial functions solves the Euler-Lagrange equation. The last paper in the list I showed you at the beginning concerns, in fact, a similar case for P here, P, D minus P, and you notice more or less of this form. But they need a stronger assumption. The K equals 2 is still open. I wish to say half a word about also about this symmetry result. Here P is 2. Again, we are in the Hilbertian case, but we have some weight, in fact, here in front of the gradient. The Euler-Lagrange equations are, this operator is weighted Laplace operator, let me say. Now, so we have an Euler-Lagrange equation, this Euler-Lagrange equation, any minimizer for PA, if it exists, okay, is a solution of this Euler-Lagrange equation on Rd up to a Lagrange multiplier. Great. But this theorem, it is proved that if K is greater or equal than 2, okay, this is natural in a sense. If A is non-negative, and if U is a smooth, say, a C2 solution of this equation, but outside the singular set, but we need something about U. So U is a classical solution of this outside the singular set, but it has some LQ, it lies and belongs to some weighted, the appropriate LQ space, then U is cylindrically symmetric. And this implies that any minimizer of the Maz'ya constant, if it exists, and it exists, is in that case cylindrically symmetric as a consequence of this theorem. Oh my God. And this is in fact obtained via the functional change I showed you before. And so when you used the moving plane method for positive solutions of this equation in Rd minus the singular set satisfying this integrability assumption. The solution V in principle might be singular at the origin, but that's not a problem, as I've learned from this nice paper by Susanna Terracini. Next, this is more or less, of course, I'm available if you are interested in something. I had no time to describe all the possible results one can meet in the literature. I prefer to list a few open problems. I already said something. I already drew perhaps your attention on some other problems, but let me propose them again in case. Now we saw that if the rearrangements we have that if A is equal to 0, okay, if A is equal to 0, then the Maz'ya constant is equal to the Maz'ya constant on cylindrical functions. Also, we have that if P is equal to 2 and A is negative, then the last result I showed you before gives you this equality in case P equals 2. I'm wondering if this equality holds for any P between 1 and infinity, provided that A is negative. And to this end, I have the feeling that this weighted version of the rearrangements inequalities might be useful. Symmetry breaking, okay, in this paper with Marita Gazzini via easy considerations, we proved that a symmetry breaking phenomenon appears, okay, the result with Marita is for P equals 2. In fact, for if A is large enough and surely positive, then symmetry breaking phenomenon appears. That is, MA is strictly smaller than MA on cylindrical functions. The same computation here with a little bit more care can be used to prove that for any P between 1 and infinity, you have symmetry breaking provided that A is greater enough. Symmetry breaking phenomenon for the spherical case is completely understood because of a series of papers, starting with the paper by Felle Schneider, but also Maria Esteban, Gabriella Tarantello, Loos, and so on and so forth. They had very, very remarkable contribution in the understanding of this symmetry breaking phenomenon in the purely symmetrical case. Now it will be great to find that the precise value of the parameter A positive for which you have symmetry breaking. But it would be in any case nice or interested to try to improve this very rough estimate we had in this paper with Marita Gazzini. Next, let us go to critical exponents. This is a problem I already said. Is it true that this constant is not achieved in the critical case if A is too large? Of course, it would be the case to investigate. Also in the Hilbertian case, to give an answer here, is it true that the picture is like that or not? Up to now, there is no answer about this interval D, the critical dimension, K is equal to 1, A between 0 and 1. Up to now, there is no answers. But okay, I had in fact a longer list of open problems, but I would like to conclude with the fractional Laplacian. Why not? Two facts about the fractional Laplacian. Here, by fractional Laplacian, I mean the standard Dirichlet fractional Laplacian for functions on Rd defined via the Fourier transform. Great. If 2s is smaller than d, then you have this unweighted Sobolev inequality. Also in this case, the Sobolev constant is explicitly known. It has been computed by Ernst. A more recent result has been proved by, okay, we also have Hardy type inequalities which are related and so, but I will not deal with Hardy type inequalities for functions, compact functions, or for functions in this space. Rather, I am interested in this Hardy type inequality for functions having support in the upper half space. What does it mean? It means that with respect to all I said before, I take k equals 1. So the singular set is an hyperplane and it disconnects Rd. So I focus my attentions on function defined on Rd plus. So this is the space of functions in the domain of this L2 norm of this quadratic form, which vanish on the negative space. This is my time almost over. And this Hardy type inequality has been proved quite recently. Of course, this is the gamma function, and this number, of course, is 1/4 when you take S equal to 1 in the local case. Now, in fact, in writing these notes, I was thinking to this very nice, good, new problem. And then I discovered that there is not a new problem. Okay, this is a conjecture I raise here. This is the best constant in the Hardy-Bogdan-Dida inequality in the previous slide. And the feeling that this constant, this inequality holds for any S between 0 and 1. Surely, it holds for S equal 1. So in the local case, when this is nothing but the L2 norm of the full gradient of V. And this is the Hardy constant for functions supported in the upper half space. As a corollary of the functional change I showed you before, in some corollary, I pointed out this inequality where this is the Maz'ya constant for A equals 1. And by the existence, non-existence results I've tried to describe before in this Hilbertian case about the constant MR2 star, we have that in particular, this is perhaps the most interesting case. This best constant here is precisely the Sobolev constant in the local case, when D is the critical dimension. Otherwise, it is smaller than the Sobolev constant. So this is one inequality to me that surely this holds if you take here a smaller lambda. But it would be of interest to know if this improved Sobolev or improved Bogdan-Dida inequality holds. Also, this was, for a moment, I was thinking that this was a new problem, variational problem. By the Bogdan-Dida inequality, this is the square of a norm, a Hilbertian norm. And by that inequality plus Dida, plus Sobolev, if lambda is strictly smaller than the Hardy-Bogdan-Dida constant, which is this one, then surely this constant m lambda s is positive. Great. Why don't we study this problem? The answer is because we already studied this infimum m lambda s in this paper with Alexander Nazarov, published in Nonlinear Analysis Theory, Method and Applications. And here is the result we proved there. In the local case, S between 0 and 1, okay, 2S smaller than D is a natural assumption. Otherwise, we do not have Sobolev embedding theorem. We proved that in any case, this infimum is smaller or equal than the Sobolev, correct Sobolev constant. And from this, we infer that this constant is not achieved if lambda is negative, because this becomes positive. Also, we proved that the strict inequality, if lambda is positive, the strict inequality implies that this infimum achieved. Standard, great, we are happy. Also, we observed a Brésis-Nirenberg type of phenomenon, and we proved that if 4S is smaller than D, then the strict inequality holds, and therefore this fractional Maz'ya constant, let me call it in this way, is achieved. This is the theorem we proved in that paper, but my conjecture now is that if D is a critical dimension in the sense that D is smaller than for S, then this infimum is not achieved. I'm more or less almost sure, it depends on days, but I'm almost sure at least this conjecture is true in the local case when S is equal to 1. And this is one of the results. I pointed out it corresponds to the case A equals 1 in some previous slide. So this is my conjecture. Of course, if the conjecture in the previous slide was correct, also the case lambda equals to this Hardy-Bogdan-Dida parameter constant should be studied. In that case, for lambda equals to this number, the more correct way, here there was a misprint, of course, RD, sorry, RD, because it's in a local situation. This problem on a larger, perhaps fractional Sobolev space could be studied also for, or should be studied also for lambda equals to this best constant. But this is what I just said. Not sure that a Bogdan-Dida type inequality exists in the fractional case in particular for when S is greater than 1, but I don't know if everything has been completely understood also in the case when N is an integer number. It's 1536, so I'm always very proud when I succeed in calculating the time of the talk, and okay, no, I have another small slide here. I have to say why. After 15 years, I went back to Maz'ya inequalities. That was because we in fact gain Maz'ya's inequality while studying a class of inequalities here in blue, in which radial weights and cylindrical weights are mixed. Okay, why one should be interested in similar inequalities. Eta, gamma must satisfy some assumptions, don't mind. Why one should study similar inequalities, okay? The starting motivation was because of Caffarelli's famous paper by Caffarelli and Silvestre, in which the operator, this quadratic form for P equals 2, plays a very important role in relation to some fractional Laplacian of order A minus 1 over 2. So that was our very starting point. These inequalities of this form also enter in some question concerning Navier-Stokes equations. Similar inequality have been introduced and studied by Jan Jallie collaborators in the case when the singular set has dimension 1. And I said several times, we started to study. In fact, I would like to show you the references to these 3 papers I obtained in collaboration with Gabriele Cora from the University of Bruxelles now, and Alexander Nazarov from Steklov in St. Petersburg, in which several questions about inequalities of this form are investigated. As far as I remember, this is really the last slide in my talk, so I I thank you again for your attention, for participating to this talk. Thank you so much. Grazie mille.
Let's thank our speaker. Well, please, comments, questions.
I'm sorry, if I well understood in Sylvester Caffarelli's concept paradigm, actually it was trace issue. Here you talk about not trace, you talk about inequality itself. So it is like in Rn.
Yeah. So let me keep it. Okay, David, oh my God, no. Okay. There is a variational interpretation of the, of course, of the Caffarelli-Silvestre result, which is not due, was not due firstly by Caffarelli-Silvestre, but I don't remember now. I'm sorry, perhaps Alexander can help me. Okay, what Caffarelli-Silvestre says, they say that you have to think to Rd as Rn times R.
Yeah, correct.
Or of two copies of Rn times 0 infinity. So in the notation in this talk, k is equal to 1 and n is d minus 1 in a sense. Okay, to any function u compactly supported, say for instance in Rn, you could be interested in the S Laplacian of u. U and the S Laplacian, so this operator is related, let me say x, is related to operator in the second order local operator in divergence form of this kind. Okay, this is a weighted operator.
Yeah.
This is a weighted operator if S is not 1/2, but let's say that in general it's a weighted operator. The function u, which is usually called the Caffarelli-Silvestre extension of the small function u, okay, must solve some precisely this problem.
Yeah, correct.
Okay. And related to you, in fact, you can extend this function u to be a positive even function in the last variable. But nevertheless, you can see here you have a variation self-adjoint differential operator whose related quadratic form takes this shape. Precisely, the Caffarelli, under the assumption that the n is greater than 2s, which is a true assumption only if n is equal to 1, by the way, because s is between 0 and 1.
I understood.
So U is a solution, capital U is a solution of a minimization problem with a non-homogeneous Dirichlet boundary datum U.
In this space, in y equals 0.
Yes, in the space, which is in the notation of the present talk, is this space 1, 2, basically are n plus 1 with respect to the weight. So 1 over 1 minus 2s plays the rule of the parameter a in the talk I have now. It holds this Hardy inequality can be proved. I don't remember, yes. for any u, not only for the Caffarelli-Silvestre extension of small u, but for any u in the domain of the quadratic form corresponding to this operator. So these are the inequality holds. And you can see that here we have the mixed weights, even if we started with a non-mixed weight, 1 minus 2s, 2, in this Hardy inequality, we found some mixed weight, precisely 1 minus 2s.
Ира, я на семинаре сейчас, я перезвоню.
You see?
What you said, Sasha?
No,
No,
it was a call for.
So, and then you can understand then from this inequality that, for instance, we used this inequality with Alexander to prove some symmetry breaking result for non-local problems. But from that, of course, we were trying to investigate corresponding more general Hardy inequalities. Why not putting zeta also here? And then we moved to Hardy-Sobolev type inequalities and so on and so forth. But then we discovered that also Yang Li and collaborators dealt with a special case of those inequalities. So why not studying them?
More or less understood.
More or less. I was not clear enough. I apologize.
No, it's very good. Thank you very much in any case.
I in fact have to thank you. And it is not the first time I have to thank Stiklov people.
Yeah. Okay. If there are no more questions, let's thank our speaker again.
Thank you so much.
Roberta,
let me find the Zoom, please. I'm not able to find Zoom. I don't know. I don't know where is the window. I don't know where is the window. Okay.